Alright, we're back for today. This is the Diabolic vtutor, and we'll be doing some more mixed topics. Primarily just the polynomials logs type of deal, you know? Alright. So here we go. It turns out that one of the problems I'd done last stream, was I just copied it wrong. It was basically the one with the radicals inside the radicals. So here we go. Let's just redo that one. So here is the problem. So we have square root of x plus 6 plus the square root of 10x plus 6. And the thing is, I had written 6 for the situation, but in actuality, what was the problem? It was supposed to be 3. So that's why the problem ended up being messed up. So now that the problem has been corrected, we can now do the problem. This is going to be a good situation now. So basically, it just looks intimidating. Just clear the radicals one at a time. So we have 3 radicals. Just clear the outer one first. That's the easiest one to do, honestly. So we shall square a left-hand side, and then we square a right-hand side, thereby undoing the radical, because this is the inverse, of course, of the square root. So thus do we free the x plus 6. I mean the square root of x plus 6, and then the square root of 10x plus 6. There we go, and then right here is just going to be a simple 9. Not too bad. So at this point, some people choose to move one of the radical terms to the other side. You don't have to do that. It's honestly up to your preference, but I'm just going to square it as is. So squaring this side and then squaring that side yet again to try to undo some of these square roots. So just watch out for this one. This is a binomial expansion. This is a squaring term number 1 and term number 2. So you're going to end up with 3 most immediate terms. So this one gets squared. Yes. So it is indeed x plus 6. And then, don't forget the algorithm. It's going to be this one times this term times 2. So plus 2 times square root of, and then this argument, I'm going to multiply directly to that argument since they are both residing inside the radical. So this one times that one. Follow whatever distributive algorithm you like. This is going to be 60x, so 66x inside the radical, and then lastly 6 times 6. And then we'll extend the radical all the way there. Alright, and then of course squaring the second term, that just clears the radical, so we have a clean 10x plus 6. Copy paste this side. Okay, so there we go. Let's just start moving everything over to the right hand side, except for the radical. We're going to isolate the radical, so therefore move these ones to right hand side, and then move these ones also to right hand side. So this is going to be 1x plus 10x gives us 11x. I do suggest crossing things out so you don't accidentally reconsider them. And then we have a plus 6 and a plus 6, so that's going to be 12. We're going to subtract 12 from both sides, so 81 minus 12 is going to give us a nice... Double check that. That can't be right, right? Yeah, it actually is nice. Okay, nice. And then we have this one right here. Copy paste, left over. Again, we did the 6 plus 6 is 12, and then we subtracted 12 from both sides, thereby getting the nice number. Alright. Just copy pasting the radical now. This is looking kind of funky, but okay. You know what? I'm sorry. I just can't deal with this visuals. So let me fix that up just a little bit. Oh, shouldn't have bothered. Okay. Alright, there we go. Alright, so taking a step back, it seems that the numbers are kind of big because we're going to end up squaring both sides, which is kind of unfortunate because this thing's going to get squared, which is, you know, a little bit suboptimal, but Is there a nice way to circumvent that? No, I don't think so. So let's just square both sides at this point. We're going to square left-hand side one more time to clear the final radical, and then we'll square the right-hand side as well. Left-hand side and right-hand side are going to get squared yet again, so make sure you use distributive property of exponent. The 2 distributes to this 2, thereby becoming 4, and then the 2 cancels with the square root, thus freeing it. So we have 10x squared plus 66x plus 36. Alright, and then this side is now the monstrosity, unfortunately. Another binomial expansion. We have term number 1, term number 2. Make sure you follow algorithm correctly. So this one is going to be 121x squared, and then this one times 2. That's very unpleasant. I'm going to leave it in factored form, because there might be opportunities for simplification. And then lastly, we have this thing squared. I should have done it the other way, after all. But that's okay. Alright, let's... Is there anything we can do? Can we simplify? No, this is not divisible by 4, so we can't cancel 4 from both sides. Okay, let's just distribute this to each term. So we're going to get 40x squared, and then we're going to get... pretty bad, right? 66 times 4. 264, right? Alright, and then this one times this one is, again, a very unpleasant value. I'm going to leave it in factored form. Hopefully we can simplify something, right? Hopefully. Okay, and then this monstrosity of a situation, unfortunately, we're just going to have to copy-paste. It's a lot to write, so copy-paste. Okay, and then now let's start consolidating by moving things to one side, so we could set up for zero product property. We'll subtract 40x from both sides. So minus 40x gives us 81x squared. Nice. We shall subtract that from both sides. But let me just put this on the calculator. Let me avoid putting off too far, right? So 22 times 69 is 1,518. That's absolutely wonderful. Okay, so this thing right here is 1518x. And then we're going to subtract this from both sides. So minus 264 and then minus 264 from there, which is this one. So thus will we get 1,254x. Wonderful. And then we're going to subtract this from both sides as well. So minus 4 times 36. So we're going to first square that nice number. So 69 times 69. And then we're going to subtract this one from both sides. So minus 4 times 36. That gives us a whopping 4,617. 4,617. Yikes. Equals 0. Okay. So hopefully we can start to simplify this nonsense, right? I just did a quick test. I was wondering what goes into are there any common factors to term number 1, term number 2, and term number 3? I just tested 81. I divided this by 81, and lo and behold, it actually did work. Let me check the middle term as well. Is 1,254 divisible by 81? I hope it is. No, it's not. Well, sometimes you get lucky, and sometimes you don't. Alright, well, at the very least, this one is divisible by 3. So all terms are divisible by 3, so divide by 3. That's 9 times 3, which is 27, result. And then divide this one by 3 is going to be 4, 1, and then 8. Alright, and then this one divided by 3. I have a vague feeling I messed up something somewhere along the way. But okay, we're going to use an alt strat afterwards. Whoops. So this one divided by 3, what is that? It's going to be 1, 5, wait, what? It's not divisible by 3. Is it? Oh, it is. Okay, good. So it's going to be 1, 5, 3, and then 9. Yes. Okay. So that's dividing the situation. We're going to get something disgusting like this, which, again, it's rather unfortunate. Wait, this is divisible by 3 again. Is this divisible by 3? No, it's not. Yeah, so the problem is this is just not divisible by 3, so we have no more nice situations. So at this point, this is a quadratic. We can factor it out. Let's use an alt strat for this one, because I have a feeling that just squaring straight up, keeping both radicals on the same side leads to higher numbers. So I'm going to pause it here. This is a quadratic. It is factorizable probably, but the numbers are kind of huge. I don't want to resort to a calculator right off the bat, so let us go use this the other way. So let me take this. Let me take this old work right here and then just set it aside real quick. So shrink that. I'm going to toss that aside for now. And then we'll go back to this first step and hopefully things up a little better. So first, same opening move. We're going to square both sides of the equation. So we're going to free the arguments of the first radical, of the outermost radical, I should say. So again, same opening move. We have that one, and then this one squared is just going to be clean 9. So again, instead of squaring both sides as is, what I'm going to do is I'm going to move one of these radicals to the other side. And I think that's going to make things a little nicer. But let's check. Let's check that. So I'm going to keep this one on this side. I'm going to subtract square root of x plus 6 from both sides. So thus getting 9 minus square root of x plus 6. Alright. And then now we're going to square both sides. So square that one and then square that one. So this one frees up the arguments. So 10x plus 6 is now free. Here we have a binomial expansion. So make sure you do that correctly. So 9 squared is 81. And then 9 times this times 2 gives us negative 18. Square root of x plus 6. And then lastly, this one squared. Watch out for the negative sign, because you should put, don't do this, because there's this derivative property after you square this. But oh wait, no, first things first, this negative gets squared, so it becomes positive. And then positive inside parenthetical, copy paste that one. But since it's all positive, we can drop parentheticals. Okay, so I think this one is a little more optimal than going this route, because we can actually start dragging things over the other side and start reducing stuff. So let's do that, you know. So let's move those things, those 3 terms to the other side. So minus 81, or 81 plus 6 is 87, and then we're going to subtract 87 from both sides. So minus 87, so that's negative 81. And then we're going to subtract this x from both sides, so minus x, and then minus x. Okay, copy paste the leftover, so we have negative 18 root x plus 6, and the numbers look a lot nicer now. So lesson learned, I guess. So rather than squaring it with these on both sides, I think it's a little easier just to move one of these to the other side. Separate the 2 radicals and then square, and the numbers end up nicer, it seems. I don't know if it's always true, but it might be always true. So this is divisible by 9, divisible by 9, and divisible by 9. So let us start canceling things out before we venture farther, you know, for a slightly easier time. So this one divided by 9 is negative 2. So the numbers are really nice. There are literally no double-digit numbers. All single digits. Alright, sharp contrast to what was happening before. Alright, well, might as well square both sides at this point. So we'll square that, and then we'll square that. So here we go. This one is binomial expansion, so x squared, this one times 2. So negative 18x is the algorithm, and then squaring negative 9 is positive 81 equals, well, distributive property of exponent, distribute to the negative 2, and then distribute to the radical. So we clear the negative, it becomes positive 4 times. Undo the radical, so we're going to get in parentheses x plus 6. So again, be careful with your distributions and in your exponential distributions. Alright, so we have this situation. It's looking really nice, actually. So let me block this off. Let's block off this nonsense. Alright, so freeing this thing, we have 4x plus 24. Alright, so let's clear this right here. And now let's move everything over to the left-hand side. So this one remains unchanged. We're going to do minus 4x minus 4x. And then minus 24 minus 24. What is that? 27? No, wait. 67? Whoa, that's kind of weird. Wait, is that right? No. 57, yes. Right? That's 70 plus 11. Yes, that's correct. That doesn't seem quite right. Maybe. We'll see. We'll see. So this is the setup for the zero product property, of course. What are the factors of 57 that possibly make some sort of 22? Well, factors of this one, 3 times 1, 19. What? Oh, okay, thank goodness, it does check out. Okay, so factors of 57, 3 times 19, and then 3 plus 19 gives us a 22 magnitude, so this is going to be correct. All right, so here we go. We have x paired with the 3, and then the x paired with the negative 19. Both signs are the same, both are negative. So there it is. As equal to 0. Thus do we have two solution candidates. We have positive 3, and then we have positive 19. But in the case of dealing with radicals, never get too excited with the answers. Always go back to the beginning and make sure they check out. So here we go. So does the 3 check out? We're checking the 3 first. So 3, if this is 3, then that becomes 9. Square root of 9 is 3. So this whole thing here will become 3. And then plugging the 3 in there, that becomes 30 plus 6, which is 36. Square root of 36 is 6. 3 plus 6 is 9. Square root of 9 is 3. So that confirms the first number. So that's confirmed. And then we're going to check the second answer. This one seems a little dubious, right? I don't know. So 19 plus 6 is 25. Square root of 25 is 5. So this whole thing becomes 5. And plug that in there. That becomes a whopping 190. Interesting. And then 190 plus 6 gives us 196. I think the square root of that is, what, 14, was it? I think it's 14. 14 times 14? Yeah. So the square root of that 196 is going to be 14. And then 5 plus 14 is 19. That doesn't seem right. Square root of 19 is not 3, so this is the one that doesn't work out. Interesting. We have this weird answer right here. Okay, I think that's good enough. So, strangely enough, we have this 19 that doesn't seem to work out. Yeah. So that's why it's always good to back plug in. Even if both of them end up being positive zeros, make sure you back check. So it doesn't work out. Interesting. Alright, so that's just a problem from last time that did not work out because I miscopied it. But we're good now. Moving on, of course, we have... do I want to write this down? That seems kind of a... Okay, no choice. Let me write this down. We have Vx as a function that has 3 real zeros. Vx as a function. It has 3 real zeros. Penmanship is atrocious, I'm sorry. Which of the following could be the equation of v of x? V of x, right. So we have option number 1, which is going to be x cubed minus 4x squared minus 3x plus 18. So that is first option, and then we have second option. It's going to be 3 times x minus 3 squared, cubed, minus 3. And then we have option C, which is going to be 2x to the power of 4 minus 8x cubed minus 6x squared, and then plus 36x. And then lastly, we have, I wrote C twice for my worksheet. Whoops. Last option is going to be 4 minus x minus 1 to the power of 6. Alright, so those are the 4 options. It's just standard multiple choice situation. Again, v of x is a function that has 3 real zeros, which of the following could be the equation of v of x? So 3 real zeros. I think this is a little ambiguous. They could be repeated. So basically, as long as we satisfy the fact that it has 3 real zeros, are they unique zeros? So I guess this is earlier in my problem-making career. I should have phrased this a little more carefully. I think if I were to rewrite this, I would say v of x is a function that has 3 unique zeros, unique real zeros, which could be the equation of v of x. Okay. But let's not assume too much, because it's been a long time since I've seen this problem. So we're looking at this one. It is a cubic function. We're guaranteed one solution, one real solution, so it can have up to 3 solutions. So we can't eliminate A right off the bat. This one here, it's also a cubic, but interestingly enough, if you memorize your shifting rules, this one, what's going on there? That is going to be your standard cubic function like this, but it's shifted over 3 spaces to the right, 3 spaces up, 3 spaces to the right, 3 spaces down, and then amplitude stretch of 3. So basically, if we were to do a rough sketch of B, it's going to be the 1, 2, 3, 1, 2, 3, down there. So that accounts for the shifts, and then we have a stretch of 3, so it'll be 1 to 3. So it's actually something like this. So it only has 1 real solution for B, but this it says 3 real solutions, 3 real zeros. So from this, if you know how to sketch out the graph for B, then we can eliminate choice B. Alright, but let's go over this maybe using synthetic division maybe later. Alright, but again, we can eliminate choice B. Checking this one, this is degree 4, so we have up to 4 real solutions for C, but we can have as minimally 0 real solutions for choice C. But we do have an x term for all of those, so let us factor that first. So let's see what happens. Oh, also, all terms are divisible by 2, so let's factor out 2x from all those terms. So we're going to get x cubed minus 4x squared minus 3x plus 18. Okay, so we have 1 real solution here and then 1 real solution in there, but there could be up to 2 more solutions. So this one, we're going to have to double check that. And then this is another graph where if you memorize it, it would really help you in determining the number of solutions. So if you graph this, number one, we make note, this is just a U-shaped type of deal. So if you have x to the power of 2, and let's say this is your only thing, this is y is equal to x power 2. If you have this and you graph it, it's going to look like this. Standard end behavior is upwards, upwards. But we also have the same thing if you have just plain x to the power of 6 is equal to y. So this one is going to be U-shaped. We have 0, 0, and then 1 to 1, standard movement, and then afterwards it's really goes upwards. And then -1 to +1 as well. The bottom one is kind of beveled out like so. But the important thing is it goes end behavior upwards and then end behavior upwards. So that's the base, the parental function base for x to the power of 6. But we have a shifted graph. We have number 1, it's reflected across the y-axis. And then number 2, it's shifted 1 space to the right, and then number 3, it's shifted 4 spaces upwards. So what that means is, again, we're going to plant the vertex at +1, +4. So right there, it's going downwards. It has a standard 1-to-1 movement, 1 to -1 movement, I mean. Just bevel the bottom, so it's something like this. So the graph of D is right here, as you can see from the visuals. If you trust my graphing, it only has 2 real solutions. So D only has 2 real solutions. They're not even repeated. So from graphing, a quick sketch of the graph for D, we can determine that this is not going to be the answer. So we only have 2 real options. We have option A, and then we have option C for 3 real zeros. Alright, this one looks like the easier to do of the two. Wait a minute, that's the same thing. Wait, this is literally the same thing as this one. Interesting. Why did I do that? Alright, let's just 2 birds, 1 stone, right? So if we use synthetic division on this one, then we will get the same answer for this one. But this one has 1 additional factor. So let's see what this one does. So we have 3, 2, 1, 0. Okay, factors of 18. We have 1, 2, 3, 6, 9, and 18. Very rarely will you select the more extreme one, so this is plus or minus. Using Descartes' rule of sign real quick, we have 1 sign change, 2 sign changes. Not super useful. Let's do the other sign. Negative. If we have a negative argument, what are the sign changes? This would be negative, no sign change, 1 sign change. So we have 1, we are guaranteed 1 real negative solution. Hopefully it's rational, right? Okay, so we're going to try -1. No, we're going to try -2. I mean, yeah, let's try -2. So we have 1, just extracting the coefficients, 1, -4, -3, and 18. 1, -4, -3, and 18. The numbers are not exactly super snowbally, but let's put -2. Product, summation, product, summation, product. Okay, good, it works out. Alright, and I recognize this is basically a perfect square situation. So this 0 candidate actually resulted in a 0, so therefore the factor is x minus -2. So this is a guaranteed factor. This one is the leftover quadratic. It's x squared minus 6x plus 9. I hope you recognize this. Half of 6 is -3. -3 squared, +9. So this is a perfect square. So x minus 3 squared. Fully factored form for option A. So technically option A does have 3 answers, right? It has solution number 1, which is -2, and then it has solution 2, which is +3. It's repeated twice though. So this 3 is technically 2 solutions, it's just repeated twice. So, which is why I think this is poorly worded. V of x is a function that has three. Let's put three distinct. Three distinct real zeros. So now that I've changed it by adding this little extra word, we can look at this. This is one solution. This is a repeated solution. So this one is incorrect. So it ain't going to be A anymore, which means that we only have C left. But let's double check. So again, this one fully factorizes into that one, which has two distinct solutions. So that one has two distinct solutions. We're just stealing the work from before. And this one also has a solution. So thus do we have three distinct solutions for option C. So option C is probably correct, assuming that only one answer is correct. But again, we eliminate choice B using quick graphing, and we eliminate choice D also using quick graphing. Now we could sit there and we could try to do the synthetic division for this one, and we could try to do the synthetic division for this one, but I think I'm actually not going to do that. So we're just going to rely on good old graph sketching. So again, this one, if you graph it, it's just a shifted standard cubic function. You don't have multiple bumps like this. You don't have a concavity up. You don't have a concave down and a concave up. You just have a single inflection point. So there's no room for contact for more than 1 0 for option B. And then again, this one is just going to be standard U shape. It's reflected and shifted upwards, but it only has a maximum of 2 solutions for this situation. Alright. And the reason why I want to avoid synthetic division is because that means I would have to distribute this. This is exponent 6 for binomial expansion. So that is very annoying. And I haven't really gone over binomial expansions, especially with degrees higher than 3. There's an algorithm for that one. Maybe we'll save it for another day. But for now, I think this is good enough. So C is the correct choice. Again, 3 distinct zeros. Alright, that's it for that problem. Moving on, of course. I hope this works out. We never know with these older problems that I designed. So we have A of x is a square root function. That's square root, not squirt. It's square root function. What about this function? It decreases over the interval of from -2 to infinity. Not inclusive because infinity is not a number. And then we have a table. The table below lists various inputs and outputs of A of x. Table below lists. I do like that double S sound, the repeated S sound. Various inputs and outputs. Of A of x. Alright, so here is the table. We have x value, we have A of x value. So again, you could just treat this as a y. For all intents and purposes, the function itself as a whole, just call it y. And then we have -2, 5. And then we have -1, 2. We have k, mysterious value k, -1. And then we have 7, -4. And our job is to determine the value of k, if k is a constant, right? Determine the value of k. Okay. So again, a is a squared function that decreases over the interval. So that can be interpreted in two distinct ways, right? So we have here squared function that decreases over the interval. So it could be that we have a squared function that's like this, or we have a squared function that is like that. But thankfully, we can actually distinguish between those two because of this additional information. Decreases over the interval. We are assuming that this is the domain, right? So I wish I'd said this more precisely. But from the way it's written, it's going to be not this one, because this one goes towards negative infinity. So for this one, this is some sort of arbitrary a value, then the domain is, or the what's the word? The domain is going to be from negative infinity to a inclusive. This may or may not be a, I don't know. Because this is, I didn't specify that this is the domain of the a of x function. I should have said that though. I should have said a of x is a squared function that decreases over the interval of its domain, which is comma, bracket -2 to infinity. So that would make it unambiguously this one. And then this value you know is going to be a -2. So I wish I had said it like that. So that's what I will say. Okay. So let me just say that. So let me go and make this wording a little more precise. So this is the domain. So now it's clear. So a of x is a squared function that decreases over the interval of its domain, which is from -2 inclusive to infinity. The table below lists various inputs and outputs of a of x. Okay, so now I believe it's unambiguous. Here we go. And our job is to determine the value of k. So we know this is like the start of the function. I don't know if we call this the vertex, but it's basically the tip of the situation. So we can actually count spaces, but let us not count spaces. Let us try to do it somewhat quote-unquote legitly. So let's start off by writing the skeletal equation. We have a of x is equal to, this is going to be some sort of squared situation. It has a amplitude in the front a. We don't know what this is at the moment. This is going to be some sort of x value. It's modified according to that one, right? So we have x minus some value. We don't know what this value is because this is going to be a shifted situation, and then plus k. So if this feels familiar, it should feel familiar. This is going to be similar to the vertex setup for parabolas. These are basically just shiftings from our parental function, which is this one. Y is equal to square root of x is our parental function. The a is just the affecting the amplitude. This h is going to affect the shift leftwards or shift rightwards. This plus k is either shift upwards or shift downwards. Again, we don't, right off the bat, this is just our skeletal equation. Okay. So if we know that this -2 is absolutely the start, this is absolutely the first number you have for the domain, so therefore this is the tip point of the function, right? So can we just simply put a +2 here? So here's a -2, the h value is -2 then, so we have x plus 2, right? Is it safe to do that? I think it is. If we know that this is the tip, okay? But let's not assume that. Let's not jump to so much assumptions at the moment. So what we're going to do instead is this is going to be one data point. This is going to be point 1, and then this is going to be another data point, point 2. So all we're going to do is we're going to do some plug and chug, and then probably we're going to have to work with a system of equations. Because let me change this from a of x into y. just to show you how many unknowns we have. Okay, so this is again just a skeletal equation. That will be one letter, 2, 3, 4, 5. There are 5 unknowns, but 2 of those unknowns are variables, and those are provided from this data table right there. Okay. Yeah. So if we consider that, then if x value is -2, then y value is +5. So let's see what that turns up. So if this is going to be, if x is -2, then the y one is +5. Let's just see how it looks first. Okay, not the greatest, because we have 1, 2, 3 unknowns. So I think we do need to use the gimmick. So I'll mention the gimmick real quick. Whoops, I should have just done the undo function. Whoops. Okay, well, unfortunately I can't go that far back. I've run out of undos. Indeed. Alright, so go back to the beginning. So from this one, since this is the domain, and this is literally the first valid x input we can put into our function, then therefore this is the tip that is right there. Again, I don't know if this is called a vertex, but whatever it is, I'm just going to call it the tip. Alright, so we know that. And because we know that is going to be the tip, then that kind of gives us a clue about how to deal with this sort of situation. Okay? So the tip is, again, -2, 5. Which, if we're given this as a vertex for our parabola, we can use it directly to populate our parabola. So this is just hypothetical. If this was a vertex for a parabola, then we would populate it like such, as such. This is the x value, you minus the x value, because it's opposite line inside parentheticals. And then the 5 one will be +5. And that would be how we populate the general skeletal structure for the quadratic and vertex form. But it's not quadratic, but it's going to be similar population. We're going to take this one and we're going to use it to populate those 2 values right there. So again, just similar situation to vertex form. So we have x minus -2. So again, it's opposite line inside parenthetical. This one, it just goes directly into the h, so it's minus -2. And then the 5 one is just going to go right there. Alright. This whole idea stems from shifting rules. Alright, so that's the situation. Unfortunately, we still don't know this a value, but again, if you rewrite this as a y value, pay attention to how many letters there are. There's only 1. There are 1, 2, and 3. But if you plug in 1 point, that fills out 2 letters. It fills out the x letter and it fills out the y letter, which leaves us with only 1 letter of unknown, which is the a value, which means we can solve for it. So let us use point number 2. If x is -1, then y is +2. So if x is -1, then y is +2. And that should allow us to solve for the a value. Alright. So -1 plus 1 is a very clean square root of 1. That seems almost too nice. And then since this is just a times 1, it's just going to be a. We're going to subtract 5 from both sides. So -5 minus 5. It's going to give us -3. So a value is equal to -3. Interesting. So as such, we can put this one and that one together to generate our a of x equation. So a of x is therefore equal to -3 coefficient times the square root of x plus 2, close parentheses, plus 5. So this is our function hypothesis. We should probably test it out, you know. And we're going to test it out using the third known point. So if x is positive 7, then y is negative 4. So if x is positive 7, then y should be, what was it? Negative 4. So we're wondering if this is legit. So let us test our hypothesis. Alright. So this is going to be 9 squared of 9 is 3. 3 times negative 3 is negative 9. Negative 9 plus 5 is indeed negative 4. So that pretty much confirms it. We have great confidence that this is the actual function for our situation. So good to go. So now we can just plug this in. We can solve for k. If k is the input, then negative 1 is the output. So negative 1 is the output if k is the input. And now it just comes to the task of solving for k. So minus 5 minus 5. Divide by negative 3. Divide by negative 3. Square both sides of the equation. So square both sides. We're going to get 4 is equal to k plus 2. Subtract 2 from both sides. K is therefore equal to 2. And that should be good. So determine the value of k. K is equal to 2. Alright, so that's using a little bit of properties for shifting rules to generate the function. If we didn't know that, would we still be able to solve? Probably, right? I think we could also use counting spaces to our advantage for this one, because radical functions move very regularly, very similar to quadratics, because they're, just the inverse. So let us try to observe that real quick. Hold on, let me delete these ones. So again, this problem's already done, but we're just going to be exploring potential alt strats. Clear that. Okay. So rewriting the situation, again, we're just beginning anew. So barring shifting rules, like let's pretend we don't know shifting rules. Can we still solve this? I think we can, just with counting spaces. Okay. So we still have to assume that the domain starts off here. So this one is absolutely the earliest value of x for the input, which means that we still have to assume this is going to be the tip of the function. Basically this part right here, and it goes downwards over time, since it decreases over time. So this must be the function, and then this one orientates the end behavior to positive infinity, negative 2, negative 2. So that one, I think we have to assume that. So something like that. And what's it? Okay, I think we can just simply do counting spaces. So we're moving from negative 2 to negative 1, which is just one space over. Anytime you have a one space movement, that's very useful for trying to determine the amplitude of your function, if it's a very basic function. Well, I shouldn't say basic function, but like, nothing that's too complicated. This is just a radical function, for example. It's not like a radical function times natural log, for example. So this is just a standard square root function. If we have a negative 2 to negative 1, that's a one space movement, right? So the question is, how does the y value change? Here's where the magic happens. How does the y value change? So from a negative 2 to negative 1, that's a one space movement for the x value. What happens to the y value? It changes by minus 3. And what do you know? Because the y value changes by minus 3, then we know the amplitude is going to be negative 3. So if we do our skeletal equation using this amplitude change, then we're going to get a of x. Wait, is it a of x? Yeah, a of x is equal to negative 3 times square root of x let's pretend we don't know this. And let's pretend we don't know that one. Okay, so again, we didn't think to put the tip values into those two locations. So we're going strictly off of figuring out the amplitude first. So at this point, we have y is equal to negative 3 times x minus h plus k. So we have 1, 2, 3, 4 letters, but remember, every single point that you can use provides xy coordinates. So this one, you can plug that in into your situation. So if x value is negative 1, y value is 2, you can thereby generate this single equation first. And then you use the other provided point, and you can plug that in as well. So if x value is 7, y value is negative 4. So 2 points means that you can plug in twice to generate two situations. So again, if x is 7, y is negative 4. Alright, so thus do we get two equations, and two equations with two distinct unknowns. We can therefore solve for each unknown, because this is just a system of equations. So you could use your favorite algorithm for solving system of equations. So in this situation, I'm just going to subtract equation number 2 from equation number 1. So again, subtracting this bottom equation from the top equation. So k minus k gives us 0. So thus elimination method is very efficient. And then 2 minus 4 gives us 6. And then this junk minus that junk. What do we get? We're going to get negative 3 square root of negative 1 minus h minus 3. So that's plus. So that's what we're going to get. Thankfully, we kind of touched upon this in the first problem we did with the double radical situation. This is a radical, this is a radical. But let us clear this some common factors first. So divide by 3. Divide by 3. And then divide by 3. Alright, so lesson learned from last time, right? I'm not going to square this entire, I'm going to move this over to the side first. Because again, it seems a little bit nicer when we do it that way. The numbers seem more simplifiable. Maybe that's just superstition, I don't know. So copy paste this one. Alright, so now we can square both sides. Square that and square that. So that one is gotten rid of. Don't forget the algorithm. This one times 2. And then 2 squared is 4. So that's the entirety of the left-hand side. We still have right-hand side, but that's easy. So the squaring undoes the square root. Okay, and then let's toss everything over to the right-hand side to isolate this radical. So isolating the radical, we have 4 times square root of negative 1 minus h. So this one plus this one is 3. Subtract the 3 from both sides. So we're going to get 4. And then plus h, that cancels to produce nothing. So this is actually looking really good. Divide by 4, divide by 4. Square this left-hand side, square right-hand side. So we're going to get negative 1 minus h is equal to 1. So plus 1, plus 1. So therefore h is equal to negative 2. What just happened? Now that we know h is negative 2, we can back slam that into our skeletal equation, work in progress. So again, we figured out that h is equal to negative 2. So this thing is negative 2, so this whole thing becomes plus 2. Alright, but of course, we do have two equations. We could always just back plug in negative 2. So again, we figured out that h is -2. Let's work with the easier equation. Let's work with this one. So we know h is -2, so this whole thing becomes +2. So +2 plus -1 is +1. Square root of 1 is 1. So -3 times 1 plus k equals 2. So +3 to both sides. So +3 plus 3 is 5. K is therefore equal to 5. So here we go. So this we now determine is a +5. Isn't that what we said before? Yeah, so you see how it's the same values as the tip value right here. -2, +5. The -2 goes into the parenthetical, and then the 5 goes on the outside. So all that work, if you didn't realize that this is the tip, and you could use that tip to generate the skeletal equation right there. Okay. That's neat. Sometimes, if you remember to do it, great. If you don't, then you just have a little bit more work to do, unfortunately. All right, next problem up. Let me take a quick sip of water. Okay, so hopefully this problem is more grammatically well written. So we're going to have b of x b of x is the name of our function. It's a radical function, but I'm assuming it's going to be a square root function again. So that's square root function. And it's represented, oh no, I don't need to put that. Oh, cool. Because there's additional information. So it's a radical function represented by here it is. Represented, whoops, what did I put by? Represented by amplitude times x minus h. And then +2. Interesting. Where a is a constant. It's not a variable, it's a constant, which means you can solve for it. What else are we given? And we have b of x contains some information. So b of x contains the points -1, 0, and another one. We have another one which is 3, 2. And our job is to determine the value of a and h, which basically means figure out what this equation is. Okay, so yeah, determine the values of a and h. Let me just determine the equation of b of x, since it's essentially asking the same thing. You know what? Let's be goofy. Because there are some standardized tests, like the SAT, that's the silly ass test, where they ask you something very obtuse, like what's a plus h? Figure out the value of a plus h, which, you know, it doesn't mean anything in the context of the math, but it's just one extra weird question to ask. So determine the sum of a and h. Yeah, let's be obtuse. There's no real reason to ask this, but I'm gonna ask it anyway. So determine the sum of a and h. And just to make this problem a little bit more grammatically correct, I had to also specify where a and h are constants. Constants? Yeah. And that should complete the problem. Okay, so let's zoom out just a little bit. So let's see. We have b of x is a radical function represented by a times square root of x minus h, close parentheses, plus 2, where a and h are constants. B of x contains the points -1, 0, and 3, 2. Determine the sum of a and h. So our first job is just probably figure out what the whole function is going to be, and then we're going to do the artificial thing of just summating those two values for some reason. Alright. Anytime you're given points for a function, it just usually means you just plug them into your equation straight up. So this one is going to be plugged into this, but this is not written in equation form. So let us write b of x. B of x is equal to a square root of x minus h, and then plus 2. Alright. So again, 2 points. So this is point number 1, this is point number 2. This is x value, this is y value. That corresponds to that one. And then this is x value number 2, this is y value number 2. Again, what that means is we can just plug in that one into there and plug in that one for that one. That gives us one equation with unknown a and one unknown h. But that's okay, because we can generate a second equation using the second point by plugging into there and there. So we will be able to generate one equation using point number 1, and then we will generate another equation using point number 2. And once you have 2 equations and 2 unknowns, we can solve for those individual unknowns. So here we go. We're going to use point number 1 first. Let me color code it. So it's going to be purple. So if x value input is -1, then b of x output, b -1 as an output will be 0. Alright. So let us start to put in those things. There we go. Alright, and then of course point number 2, I'm going to color code that differently. Let's use that light blue. If x value is 3, then y value output is 2. Alright. So let us fill out the rest of that nonsense. So as promised, we have equation number 1, and then we have equation number 2. 2 unknowns here, and then 2 unknowns there. We're just going to simply plug and chug and solve. Unfortunately, it seems elimination isn't perfectly optimal for the situation. So what I'm going to do is I'm going to solve for one letter and then substitute it into the other equation. So this one I'm going to solve for a by subtracting 2 from both sides. And then I'm going to solve for a by dividing this square root from both sides. So a is equal to -2 over square root of -1 minus h. So that is using equation number 1 to generate this modified equation right here. We're going to take that one and slam dunk it right there. So take that a, plug it in. It's going to be kind of nasty though. That's okay. So this is going to be -2 times that. Three minus h on the top. And then in the denominator we have the square root of -1 minus h. Glorious. And then we have plus 2. Alright. Well, here's the nice thing though. We could subtract 2 from both sides and get 0. So that's already a setup for a zero product property. Perfect. So 0 is equal to -2 times 3 minus h over square root of that nonsense. Okay. So there's something we can make note of. We can actually multiply the denominator to both sides on the assumption that this is not going to be 0. Alright. But this denominator only becomes 0 if and only if h is equal to -1. So if -1 is here, then this becomes +1 plus -1 is 0. So we say h cannot be -1 as a disclaimer. So we're going to put that right here. And once we say that, we can just solve for the top portion. So this one cannot be 0 because we will be dividing by 0. So that one, we're going to eliminate that by multiplying to both sides. And since it cannot be -1, which results in 0, then it's going to be a valid move. So here we go. Alright. We can clear the -2, but that doesn't matter. So using zero product property, how do we make this parenthetical and equal to 0? It's if h is equal to +3. So as long as h is +3, it doesn't violate this one. So our earlier move, multiplying this denominator to both sides, is valid. So h is solved for, which means we can solve for a. So h is 3. Oh, this is bad. Wait a minute. Okay. Well, let's plug it in. Let's see what happens. So if h is equal to 3, then the bottom portion is -4. What the heck? Uh-oh, this is bad. That's not a real number. Interesting. Well, it appears that something weird has happened in that did we lose a solution somewhere along the way? That's the question. Okay, well, unfortunately, we got this weird thing where a is equal to an unreal number. Alright, so here it is, -2. This one splits up into square root of 4 times square root of -1. So that one becomes -1 over I. We haven't covered imaginary numbers, but this is what we're going to get from the situation. And that's actually pretty surprising. Huh. Very interesting. So the question is, how come it came out like that, right? That is interesting. So what gives? Do we just end here because this is no real solution, or are we missing something? I think maybe we're missing something. So long story short, the setup seemed good because this is equation number 1, equation number 2. We got to a point where we were able to substitute one into the other. We have some sort of answer for h, but the a value ended up being broken because this one has negative inputs. Ooh, that's weird. Can't we plug it into the other one though? Let's see. If h is 3, we get a times 0. So that is unfortunately not useful, which means something very specific. So this is actually the tip of our function then. Yeah. Okay. Coincidentally, that's actually the tip of our function, and I think that was the gimmick to doing this particular problem. So I think the reason why everything just ended up getting all screwed up, like why did we get this one screwed up in the first place? And that's because the value we're working with right here, h is equal to 3. Oh no, that's equal to 2. Wait a minute. Okay, that's even more striking. Let me check something real quick. Let me see if the substitutions are correct first. That's always the first thing to double check. So that's -1 directly in there. Okay. And then 0 is directly in there. Yep. 3 is directly in there. Yep. And then 2 is directly there. Yep. Okay. So let me think if these manipulations are correct. Let me see. So this is just solving for a, so it is indeed just moving this over to the denominator, and we do get this one, yes. Let me double check to see if h is negative or something like that, real quick. So what happened was this one got substituted into there. So the negative 2 ends up in the numerator. Yes. This was also in the numerator. Yes. That one is in the denominator. Yes. Okay. And then we subtracted 2 from both sides. That's a valid move. And then we multiply this to the other side, assuming h is not negative 1. So that's also doable. And then we solve for h. H is equal to positive 3. Okay, interesting. We're going to set this aside for a moment, because I think this is going to be a gimmicky problem. But let me confirm my suspicion. Again, I think this is going to be the tip of the radical function, because we know this is going to be some sort of square root function. So it's like this, or it could be like that, or it could be like that, or it could be like that. So there are only 4 main motifs we can possibly get with this type of function. And here's the thing though, we have a plus 2 right here. Remember, just like how we have vertex form, this one and this one in conjunction, these two in conjunction, in tandem, is going to give us the tip. For regardless of whatever situation, whichever one of these 4 situations we have, this one should always give us the tip. Which means what? Which means that extracting it from here directly, the tip should be negative h comma 2. Right? I'm sorry. No negative h. It's just positive h. So positive h comma 2. And that one is already given an output of 2. Because there's only one y output of 2 for this type of function. So therefore, does it feel kind of shoddy? Maybe. Since this x value is 3 that results in that's 2, then this h value should be equal to 3, right? Which is exactly what we found right here. H is equal to 3. So that's very interesting. So if h is equal to 3, then we should be able to solve for a, right? Which means we have to use the other equation. If we try to use this equation yet again, it's not going to be informative, because that's how we generated this 3 in the first place. So let's go off of that. Alright, so we are in agreement that h seems to be equal to 3. We're going to have to double check that afterwards. But now that we know h is equal to 3, let's just solve for it using this leftover situation right here, right? So we shall combine this information with our work in progress to generate the final equation. So we are going to get what is it? A times square root of, if x value is negative 1. Let me just color code this. And what do we else have? We have minus 3. Figuring that the h value is 3, so we have minus 3 inside the parenthetical, inside the radical, and then we have plus 2 on the outside, and it should be equal to y output 0. So single unknown, single equation. Yeah, that's a problem. You see how we have this square root of a negative 4 inside there? So that's not going to work out. So unfortunately, this problem is kind of trashed. That's kind of unfortunate. Well, I guess that's what I get for... I think I was sloppier in making these type of problems back in the days. But again, the most we can do is we subtract 2 from both sides. And then we clean this up. Unfortunately, there's just a negative inside the radical. So I think this one is miswritten. I don't think it's supposed to be negative 1. It's probably supposed to be something else. No, it still doesn't fix it. Even if it was positive 1, we still get a negative inside. So, maybe this is supposed to be plus. Yeah, I don't know. I don't know what happened. But this problem is scuffed. But the overall methodology was correct. So the take-home message is the strategy was correct, but then the conclusion is erroneous because the problem is scuffed. Yeah, so it's undoable. So I think this one just doesn't even, strictly just doesn't work out, unfortunately. So we'll take it for what it is. Alright, well, that's unfortunate. VOD watchers would just have to skip it, unless I miscopied something. Hold on, let me double check. So there is a chance I may have miscopied something. -1, 0, 3, 2. No, that looks correct. Alright, well, regardless, I do wish to emphasize that this one, you can assume that it is a tip because this is the y value plus 2, which corresponds to this one. So this 3 should correspond to in there. So this, it's just that this value here is wrong. This one needs to be changed. It would need to be changed to, yeah, it can't be 0. I think that's just, wait. Yeah. Okay. Well, that's that for that particular problem. Maybe I'll come back and fix it at the end. But for now, we shall skip it. We have another problem, and hopefully this time it's doable, right? Alright, let us see. So we have next problem up. The vertex of a radical function. Again, I don't know if it's called the vertex. I'm just using whatever words I think is correct, but I was going to put the tip. Just the tip. The tip of a radical function. I'm going to rephrase it as a square root function. Just to be more precise, because I think radical function is technically ambiguous. And this function is called c of x. And that tip is going to be -1, -4. So because we're given the tip, we can use that to generate the skeletal equation for this radical function. Alright, and then we have if 8, 2 is a point on the graph of c of x. What is the equation of c of x? Okay, so we're given that one. Again, we're told that this is a square root function. And we're given the quote-unquote just the tip is -1, -4. And we're given this is a point on the graph. So here is the plan of attack. We can use this fact that it's a squared function in conjunction with the tip of that function to generate the skeletal equation. So let us write c of x is equal to skeletal equation. It's going to involve some sort of square root situation with x. This is the x coordinate for the tip, and this is the y coordinate for the tip. So this one is going to be opposite land inside parenthetical, so it's going to be +1. Just like how we do it for the parabolas, right? So -1 plus 1 gives us a 0 argument. So that's just the shifting rows. And the -4 is on the outside. And you notice I left space here. That's because we don't know the amplitude. Which is why we're given point number 2. Point number 2 will allow us to plug in x value, y value. So this one will become 2, and then the x will become 8. And once we plug in that point, we have one unknown left. That allows us to solve for that unknown. So let us do it like that. So +4 to both sides. Then we get 6. 9. 8 plus 1 is 9. And thus we can solve for a. So we get 3a is equal to 6. So a is therefore equal to amplitude 2. Alright, and I think that finishes the problem. That was so much faster than the previous. But let us merge these two so that we can write the full answer. So c of x is equal to, amplitude is 2, times square root of x plus 1, close parentheses, minus 4. So again, here's the problem. We have successfully generated the equation right there. So just to review the strats, we took advantage of the fact that we're given the square root function and we're given the tip of that square root function. That's basically this part right here, right? So we were given that one. Because we're given that tip right there, we can use it to generate the skeletal equation. So you can see this is the tip, and that we use to populate those portions right there. And then of course, we don't know what the amplitude is, but because we're given this additional point, we can plug in 2 and 8, and that allows us to solve for the amplitude. And once you have those ingredients, we are basically done. Just use it to populate via substitution. And then we're good to go. So that was pretty straightforward for 5. Let me grab another piece of paper so that we get to the next batch of problems. Okay, and this is going to be some sort of random problem in no particular order. We're told that f of x is equal to we have 6x squared plus ax plus 2x minus 15. And here is the little disclaimer, a is a constant. So this is fairly standard practice on standardized tests, and like the SAT, like the silly ass test. So a is a constant. It's just to say that this is not a variable. Alright. If one of the zeros if one of the zeros of f of x is, here's the funny thing, 8 minus a, comma, what is the other zero? So not exactly standard vernacular, but I wrote this as best as I could. So we have some sort of quadratic equation, because you know this is going to be x squared, this is technically x power 1. If we knew what this a value is, it's a constant, we can combine those two particular terms to make just one x term. But you know, this is a gimmicky problem, so we don't know what this is. And then we have a constant right there. So quadratic function, we are told that one of the zeros of f of x is this one. And make sure you remember the definition of what a zero is. What is the definition of a zero? It means if this is a zero, if we plug that into our function, then that should generate a zero. Isn't that great naming schemes? Alright, so let's take this 8 minus a, and then we're going to slam dunk that into f of x. And again, the output should be equal to 0, because that's what it means to be a zero of a function. So if I was being particularly annoying, I could have called this one a 0 instead. If one of the solutions of f of x is x minus 8, what is the other solution? It's going to be the exact same thing. So I'm going to leave it as it is, though. Alright. So again, we're just taking 8 minus a, and we're plugging it into our function f of x, which means all the x's will become 8 minus a. So a little bit of distributive property. Nothing too exciting, though. So we're going to have a 6 in parentheses 8 minus a squared. Again, this is just x value replacement with 8 minus a. And then we have this one right here. So plus a, we don't know what a is, of course. 8 minus a. And then plus 2 times 8 minus a. And then lastly, minus 15. It's right close to the edge. Let me move things over just a little bit, because it's too close to the edge. Alright, so all we did was we just plugged in 8 minus a, and we set it equal to 0 because that's what it means to be a 0 of a function. So we just have a little bit of cleanup to do. So copy paste the 6, standard binomial expansion, so it's going to be, I'm going to do it kind of backwards, so negative a squared is a squared, and then this one times 2, minus 8 times 2 is 16, then 8 squared, 64. So first distribution and then second distribution, I'm going to put this one in alphabetical order-ish, with the variable first, and then this one times this one. So greater degree first is what I like to do. Most people like to do. So distribute this one to this one, we get negative 2a. This one to that one, 16 minus 15. Alright, so a little bit more distribution to contend with. So this one distributes to this one, and that one is 96. Almost nice. Reverse nice. It's, yeah, 96. And then 6 times that one, kind of unpleasant. Carry the 2, 38, yes. 38, 4. Okay, that's a minus a squared. Cross it out. These two are combinable, thereby giving us plus 6a. So it gives us plus 1. Alright. It's still equal to 0, because again, that's the definition of a 0. So these two are combinable. Oh wait, that's a minus. I almost screwed up. It's 6a squared minus a squared. And then this one, plus 6, opposite signages. So we have 90a. Then lastly, we have this one right here. And there we have it, just a quadratic problem within a quadratic problem. So oh, these are all divisible by 5. Okay, good, perfect. So we're going to factor 5 from each of those, thereby getting 5 times a squared minus 18a plus, that's 77, yes, we do 0. Alright, so both signs are the same, both are negative. It's just 7 and 11 to make, yeah, checks out, 18. So we have 7 and 11. We don't need to copy the 5 because it's not a variable. Alright, there we go. So therefore, a is equal to positive 7 or positive 11. Two answers, maybe. But make sure, you know, we gotta double check the situation. What do we figure out? Oh, we figured out what a is, so therefore we're just gonna plug it into there, right? Wait, is that what we want? Oh, wait. Yeah. Let's just put it in there. Okay, so if we plug in 7 into here, the whole thing becomes 1. So the 0 that we were given, which is 8 minus a, now that we know a could be it could be 7, then the 0 candidate would be 1, because again, 8 minus 7 is just 1. And that means that the other 0, assuming that this a value is correct, is 8 minus 11, which is negative 3. So this one could be our scenario. We're going to have to double check that, of course. But what if a is equal to 11, right? Wait, these are two different situations. I'm sorry. So if, we'll call this scenario number 1, and then we'll call this scenario 2. So if a is 7, then that 0 that we're given is 1. That's for scenario 1. But if we have scenario 2, if a is equal to 11, then that 0 that we were given is actually -3. So which of those is the correct scenario? Which means we have some more work to do, unfortunately. Right? Okay, so let's color code this. We're going to color code this as the blue scenario. So assuming that a is equal to 7, then we're just going to combine those two together. So we're going to get 6x squared plus 9x minus 15. So is this a nice situation? Yes, we could factor out 3 from each of these terms, thereby getting this. This is very blue. Alright. Factors are different signs, and the larger of the two is positive. We have 2, 1, and then we have 5 and 1. That does produce a 3 in the middle, so that's good. Okay, so we're going to have a 2x, which gets multiplied to the 1, and then we have a 1x, which gets multiplied to the 5. This is the smaller of the two, so it's negative, and then the larger of the two is positive. Alright. Again, this is scenario 1. If a value is equal to 7, then 1, 0 is 1, which confirms that's the one we were given. And then the other 0 is going to be -5/2. So that's the second 0. If the first 0 was 1. So this one seems like a legit situation. And then let's check the other situation, of course. This is now scenario number 2. What if the a value was 11? That means that the first 0 would have been -3. Which means we have put in 11 right here. So if a value is equal to 11, then 11x plus 2x gives us 13x. And then we'll copy paste the other two terms. Alright, is equal to y. And then we can't factorize something from all three terms, so we have no choice but to use our algorithm. 6, 1, 3, 2, factors of 15, 15, 1. Probably not this one. And 3 and 5, probably this combo. So we have 9 and we have 10. Nope. We have 18 and then we have 5. Yep. Alright, so it's going to be 6x that gets multiplied to the 3. And then the 1x gets multiplied to the 5. Signs are different. The larger of the two is positive, so this is the larger of the two, so it's plus. This is the smaller of the two, so it's minus. So we have answer number 1, x is equal to -3, which is the one we were given. And then we have the other answer, which is 5/6. That's weird. I did not expect 2 scenarios. Okay, but that's what I get for these old design problems. So what does that mean for us? It means we have 2 possible candidates for the a constant. Yes. So solving for the situation, we figured out 2 potential values for a. A could be 7 or a could be 11. So if a is 7, then the first 0 is 1, which means the second 0 is going to be -5/2. So that's scenario 1. But then if the a value is actually 11, then the first 0 is -3, and then the second one will be 5/6. I don't think anything is violated in these situations, because this one has the domain for this is all real numbers, so I trust that these 2 scenarios are correct. But you have to pair these 2 together. Those 2 are 2 zeros for one situation, and then these 2 are 2 zeros for another situation. So don't just put them all in like one row. So if you were writing your answer, don't just put like, oh, it's -5/2, 5/6. So this would be poorly written. So make sure you associate this 0 pairs with that one, and then that 0 pairs with that one. So that is the answer. Or rather, those are the two answers. Okay. That was kind of interesting, I guess. And of course, we're going to move on. We have, do I wish to do factoring problems? Not in particular. Now here's a topic we haven't really covered, honestly. But it just has to do with polynomials. So we didn't cover this directly, but in a way we did touch upon it as we were doing graphing of polynomial functions. So I think it's okay to go over this. So the problem is we have a degree 4 polynomial. So a degree 4 polynomial, and this has a very specific meaning, has zeros I'm not sure if this is a standard way to express this, but a degree 4 polynomial has zeros. Let me not put at. It has the zeros, -5, comma 3 halves, comma, and 2. What else? If the polynomial g of x, okay, this is really written strangely. So then this polynomial is called g of x. Yeah. So a degree 4 polynomial g of x has zeros, -5, 3 halves, and 2. Interesting. And then we are told very specifically that g of -1 is equal to negative. Oh, I almost messed it up. I don't know why I put a -1. It's only positive 1. So g of +1 is equal to -6. What is the equation of g of x? Okay, so I feel this problem is maybe a little poorly written, but it seems all my older problems are kind of poorly written, or a good number of them. This is when I wasn't as careful with my grammar. I think nowadays I'm a lot more careful. The more precise you are with your grammar, then the more precise the translation will become. So let's look at this as it is. So a degree 4 polynomial g of x has zeros 1, 2, and 3. So here's a question though. Are those the only unique zeros? Which means that one of them will be repeated, right? Because it's going to be a degree 4 polynomial. This is 1 distinct 0, 2 distinct 0, and 3 distinct zeros, but we can have a repeated solution. Because again, this one only gives us 3 real solutions. So I think there is a rule that we should have one more real solution since this is degree 4. Yeah. Which means one of these is probably repeated. So I think that's the interpretation I'm going to go with. Another interpretation is these 3 zeros are the ones that are given, and then you have an unspecified 0. We'll call it unspecified 0 p, right? We don't know what that one is, but I don't think I'm going to write a problem. I don't think the problem is that one. So let's just assume that these are the only zeros that are given for the function, and there are no other. There's no other 0 that's not one of these 3. So long story short, from the sentence we have 3 distinct zeros. One of them will be repeated since this is a degree 4 polynomial. So that's how I'm going to preface the problem. Alright, and then of course we're given this funny situation. What is that for? Probably for figuring out the amplitude. So determine the equation of g of x. So let me think about how I can make this wording a little better. Degree 4 polynomial has only the following zeros. Yeah, there you go. Okay, unfortunately there's no more space. So only the following zeros. And I think that's going to clear the ambiguity. Alright, but unfortunately the spacing is now incredibly awkward, so let me move things over. Well, if only I had pre-written these things, right? That's okay. For VOD users. I'm going to timestamp it so we begin at the most optimal stage. Alright, there we go. Okay, perfect. Zoom in. So we are going to, here is the fully written problem. We have a degree 4 polynomial of g of x has only the following zeros. Let me put the colons. -5, 3 over 2, and 2, which means one of them is going to be a repeated solution. And then we have g of 1 is -6. Determine the equation of g of x. Alright, so what that means for us is this one, we're going to use it to populate our skeletal equation. So since -5 is a 0, that means x plus 5 is the factor. So we can flip from zeros into factors. And then we have this one right here. If that's the 0, then the factor is x minus the 0. So it's -3 over 2. And then lastly, we have this one, which means it's going to be x minus 2. Close it. And here's the thing, we don't know what the amplitude is. There's some sort of amplitude value here. Again, we don't know what it is, but it is a number. So that is equal to g of x. And then the other thing to make note of is we don't know what the multiplicity is. We don't know if this is the one that's 2, if this one's the one that's 2, or this one's the one that's 2. Like, which of those exponents is the repeated one of 2? And then if one of them is 2, then the other one should be just 1. Let me put this as p. Alright, so again, we don't know if n is 2, if m is 2, or if p is 2. But we know that if we plug this in, then it should be true for the situation. So I feel like this is not a well-written problem, but let's see. Maybe it turns out okay in the end. Alright, so given this factoid right here, if we plug in 1 for the x value, then the overall output will be -6, right? And hopefully things don't go awry. So I'm going to change everything back. So +5 here. And then this is -3 halves there. And that's -2 to the power of p right there. And that should, times a, don't get times a, is equal to 6, -6. Alright. So this negative here could be accounted for from multiple, I feel like this is multiple answers to this situation. Yeah, I don't think this is a well-written problem. Okay, well, we'll try our best. So this one right here is going to be 6 to the power of n. Again, we don't know if this is even or odd. This right here is going to be -1/2 to the power of m. So that one, again, it's not very clear. This one is going to be -1 to the power of p. Okay. So unfortunately, we don't have a super useful situation, right? I think this is going to be one of those artsy-fartsy problems. Unfortunately, So again, I don't think this is a well-written problem. So we can only come up with a candidate for g of x. We don't know if it's going to be the definitive equation for g of x because again, this information is too ambiguous. So this is what we have, and now I guess we could just use guess and check kind of situation, right? So all we have to do is make two of the numbers into exponential 1, and then we only have to make one of them into 2, and we'll see if it works out. So what that means is we have potentially 3 scenarios, right? So you don't have to show all the work, but I'm going to write it down anyway. So assuming that the first one is going to be 2, then the second one is going to be 1. And we're just going to run through each of those 3 scenarios. So it's not going to be too difficult, but it is kind of annoying though. So that one's one scenario. So that's if that's 2, 1, 1. But what if this isn't 1? And then the second one is 2. And then the third one is 1. So that's second scenario, and then third scenario. What if this one is 1, that one's 1, and this one is 2? Hold on, my roommate's contacting me for dinner. So this will probably be the last problem. Okay. So again, we'll call this one scenario A, we'll call this one scenario B, and we'll call this one scenario C. And we're just going to determine if these are doable situations. So again, not a well-designed problem, but we'll try our best. So this whole situation is going to transform into A times 36 times negative 1/2 times negative 1 is equal to 6. So this is a workable situation. So number 1, the 2 signs will cancel out. And then 36 divided by 2 is 18. So 18a is equal to 6. So therefore a is equal to 1/3. So that's for scenario A. So this one seems like a legit situation. Checking scenario B, of course. Is that a possible scenario? So just simplify this junk. We're going to have a times 6 times 1/4 times negative 1. That's equal to negative 6. Oh wait, I think for this one I dropped the negative sign. So these two negative signs cancel, but this one does not. So this is still negative, that's still negative, and that one's still negative. Okay. For this one, let me double check. 6, positive 1/4, negative 1, and then negative 6. So the two negative signs will cancel out. And divide by 6, divide by 6. So a is equal to positive 4. And that is for scenario B. So that works out. And then scenario C, let's see if this one works out as well. So we have negative here is canceled to make positive 1. We have a negative 1/2. And we have a 6a. Alright. Well, canceling this 6 with that 6 gets us negative 1. Canceling the negative sign with that negative sign. And then we have half a is equal to 1. So therefore a is equal to 2. So that is scenario C. Okay, and there we go. So depending on which scenario you want to go with, we can have a value as negative 1/3. But this situation A is when we assume the multiplicity of that one is going to be 2. But then if we assume that the multiplicity of the middle factor, the red factor, is 2, then our A value has to be 4. And of course, if we assume that the multiplicity of the magenta is going to be 2, then we have scenario C where the A value is 2. So yeah, we have 3 distinct situations that could possibly be true. So when it says determine the equation of g of x, it should just be determine a valid equation. Yeah, because we have three options off the top of my head. But yeah, so any of these three, all three of these scenarios potentially work out. And I think that's it for this particular problem. Okay, which means that we're going to be done for today. Because my roommate wants to go get dinner, and then I also want to go get dinner because I'm actually pretty hungry by now. We're probably going to be eating some hamburgers. Yes, hamburgers. So I'll see you all maybe another time. Maybe later tonight, but I keep saying that. But hopefully I'll do another stream later tonight. But that'll be it for now. You have a good one. See you next time.